Good morning, gentlemen. Today is Tuesday, April the 21st, and today we are going to start the next unit, which is all about magnetism. Um, this goes along with electricity, but we are now done talking specifically about the electricity unit. And from this point forward, we'll be moving on into our next unit, which is magnetism. Be aware that your quiz on Friday will cover electricity. So you'll have a question on series circuits and a question on parallel circuits for this Friday's quiz. However, in the meantime, we're going to start the next unit, which is magnetism. And today we're just going to talk about the properties of magnets. Now, unfortunately, at LaSalle, I have a whole bunch of magnets and other things that I could use to show you the properties of magnetism and that sort of thing. But in the meanwhile, you're just going to have to kind of play along and use your imagination. I know that you've been exposed to magnets in the past. You've played with magnets in your lifetime. And so none of this stuff should be a real surprise to you at all. At least I hope not. In any event, the reason that we talk about magnetism now, right after the unit on electricity, is that magnetism is a force that exists between charges in motion. Now think about this, all right? What is a charge in motion? Well, it's an electron or a group of electrons or possibly protons, but mostly electrons that are moving from one place to another, all right? Where else would you be able to find moving electrons more easily than in an electric circuit? However, that's getting ahead of ourselves, at least for a little while. All right, we'll talk about electromagnetism tomorrow. For now, let's just talk about magnetism in and of itself. It is a force, all right, a push or a pull that exists between charges in motion. Now, what do we know about magnets? What can we tell ourselves that we know about magnets? Well, we know an awful lot. At least I think you do. From your 8th grade physical science classes with Mr. Maloney or wherever else you may have taken a physical science class, you know a couple of different things. First of all, a bar magnet, a long piece of metal that is magnetic in nature, has two poles, okay? And we refer to these as a north pole and a south pole. That's what the N and the S shown here are shown. So magnets are polar. They have opposite ends. And so if you suspend a bar magnet from the ceiling, and in our classroom, I usually literally tie a string to the ceiling and hang a magnet from it, and eventually you'll see that it will orient itself so that one end is pointing toward the north of the Earth and the other end is pointing toward the south of the Earth. And that's why we call the poles of magnets north and south. Now, the physical poles cannot be separated, all right? You can't have a magnet that's just a north or just a south, okay? If you take the bar magnet here and let's say you cut it in half, then you end up with two little magnets. There's an the south pole there and a north pole there, all right? I'm terrible at writing with this silly mouse, but anyway. Now, what else do we know about magnets? We know that like poles repel each other. So if you try to put two norths together, they miss. They won't. It's very hard to hold them together. But opposite sides, like north and south, would attract or do attract one another. The principle that we talked about in terms of suspending a magnet is the principle behind a compass. All right, this is a little compass that came off one of my kids' backpacks, but it works reasonably handsomely. And a compass is simply a little magnet. The needle in there is a magnet that the south pole of the magnet is attracted to the northern end of the Earth, and the north pole of the magnet is attracted to the southern portion of the Earth. Permanent magnets are composed of aluminum, or aluminium, as the British say, cobalt, and nickel. All right, we call them ferromagnetic, which is interesting because iron in and of itself is not magnetic, although we can get it to become magnetic in the presence of a strong magnet. All right, so if you put a piece of iron near a magnet, they will, or it will, attract to the magnet. Okay. All right. So moving along, the next thing that we need to discuss is what we call a magnetic field. Now, in the previous slide, you see all of these lines here and here. These are what we call magnetic field lines. And so, what is a magnetic field and what are the properties of magnetic fields? All right, well, let's look at the picture that's coming up now, a different picture. This one is kind of cool because it shows not only the bar magnet on the right-hand side, but it also shows that the Earth is actually a magnet as well. All right, it's got a North Pole and a South Pole here. I know that the image is a little bit blurry. I don't know why that is, but I couldn't get it to be any clearer. So a magnetic field is found in any region, any area, any space where a magnetic force may be detected. Okay, so any place that you feel a magnetic field, that is a feel a magnetic force, you're in a magnetic field. Now, its direction is the direction in which the north pole of a compass would face. Now, this is where it gets a little tricky. The north pole of a compass faces north, but we just said the opposites attract and that sort of thing. So what happens is when you make a compass, you actually put an N on the south pole of that magnet, of the magnet in the compass, okay? And you put an S on the north pole. That way, the S points toward the south, okay? Because the north pole of the magnet points toward the south pole of the Earth, and vice versa, right? It's a little confusing, but think about that. You'll understand. Now, so the direction of the magnetic field is the direction in which the north pole of a compass would face. So look at the arrows here. So the field lines actually go out and around, and they're going this way, from south to north. And the same thing is true in this magnet. The arrows are going this way. I didn't do a very good job on that field line, but you get the idea. Notice also that they never cross, all right? None of these lines cross any of the other lines. And their density indicates their strength. So think about this. Is the magnetic field of this magnet stronger here, where the distance between field lines is this much, or here, where the distance between field lines is this much? Well, it's going to be stronger here. You're going to try to make, I'm going to try to write stronger. Check that out, huh? All right, stronger, stranger, something. I don't know. Anyway, so the density indicates the field strength. And finally, although you're going to love this, we're not doing any math in this unit. Okay, love that, right? The units for magnetic field strength are given in what we call Webers. Okay, Webers. All right. That, my friends, actually concludes our discussion. I know the presentation is still running, but this is actually the beginning of tomorrow's lesson. So there is no homework for tonight, although I will post another combined circuit problem so that you can have a good look at that. All right. So have yourselves a happy Tuesday, and I will see you tomorrow.